Once you've learned about limits, you're at the point where we're ready to answer a question of antiquity with mathematics. And that is, what is the idea that we can use in order to find the slope of a tangent to a curve at a specific point? Remember, we were able to find the slope of a line, but if we had a graph that curved, then it was a whole different ballgame in terms of finding the slope of a tangent line to a function that curves. And this was a question for a long time in mathematics until that breakthrough with limits occurred, and then we were able then to make that link up to be able to get a process that would generate a new function where the function of the output of this new function would actually be the slope of the tangent line to the original function at that given x. Now, when you're working with this process, we first look at our definition of the derivative, and that's what this video works with. But then after that, we'll look at rules of differentiation. And the rules of differentiation just lets us have some patterns that people have recognized from doing this definition process, and then have let us, with the theorems and the properties for our derivative rules, to be able to come up with these a little bit quicker and without having to go through the definition of the derivative process. So what I want to kind of reiterate to you is that when someone asks you to use the definition of the derivative in order to get the derivative, then you want to go through the process I'm going to show you on this video. If they just say find the derivative and you're allowed to use the rules of differentiation, you would want to go that route instead of the definition route. So let's look at what this says. The definition of the derivative of a function. So the derivative of a function f at x is, the notation for derivative is a prime on it, and then there's other derivative notations that I'll mention at the end. But it's f prime of x. So if someone says f prime of x, they're actually asking you also to find the derivative of the function. And it's equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. There will be certain textbooks or certain times that this will be presented to you with the letter h instead of the notation delta x. So this could also be said the limit as h approaches 0 of f of x plus h minus f of x all over h. Same idea, just two different notations for that little increment on x. Now, that will be the derivative whenever the limit exists, so that limit has to exist. And the function f prime of x, this function f prime of x, gives us the slope of the tangent to the line, slope of the tangent line to f at the point x comma f of x. So this actually does that slope of the tangent line that they were searching for. And it's provided that the tangent line exists. Now here's some other notation. So f prime of x is one of our notations. dy dx, that's the derivative of y with respect to x, asking the same thing just with a different notation. Or the derivative with respect to x of f of x is another way they could ask you to do the same process of finding your derivative, or the derivative with respect to x of the expression y. All of these are asking you to find the derivative, and if it's asked of you by the definition of the derivative, you're going to do the process that I'm going to show you in this video. If they ask you to just find the derivative and they don't say you have to use the definition of derivative, then you would apply the derivative rules. Now, here's what it's actually doing. So this purple line is tangent to my function f of x at the point x. So I was seeking, or they were trying to figure out what the slope of this purple line was, tangent to the function at x. We know that when we were working with slopes of lines, though, we only knew how to find the slope of a line if we had 2 points that it went through. So from the x, they stepped over a little bit, x plus an increment in x, So that's your delta x. And it could have gone left or could have gone right, depending on if delta x is positive or if delta x is negative. But we're just going to do if delta x were positive for our pictures. Now, when you go over to get a new x value, you can reference that back up to the function. And we are going to state the x, y coordinates in function notation of the purple point that we're interested in finding the slope of the line, and then this other point we had to create to get 2 points. So this purple point, x goes in the function, f of x comes out. So that's x comma f of x. Now for this other point, we went over to x plus delta x. So x plus delta x is your input. And then you run that through your function, and your function is y equal f of x. So when you run that through your function, this is going to be f of x plus delta x. Now, I know that when I have 2 points, and I'm looking at the line that goes through the 2 points, well, if I'm using 2 points from the curve, then it's a secant line. And so this line, my slope of my secant line, well, to find the slope of a line through 2 points, it's the difference in the y coordinates divided by the difference in the x coordinates. So you want to think of this as your x sub 1 and your y sub 1, and this your x sub 2 and your y sub 2. So remember, slope is the change in y's over the change in x's. So my slope of my secant line, using this notation, is f of x plus delta x minus f of x over x plus delta x minus x. Now when I simplify that, my slope of my secant line is f of x plus delta x minus f of x all over, and then in the denominator, my x plus delta x minus x, I get that simplifies to delta x. And this is referred to as the difference quotient. And they were stuck with that until they realized that, well, if I didn't walk that far over, if I just had an x plus delta x that was closer, that secant line would have a slope that's actually closer to the tangent line's slope than the original one that I had. So if my delta x was increasingly tiny, if I was just stepping a tiny bit over from the x instead of that far over, then the slope that I would get out would be closer and closer to the slope of the tangent line. Well, how am I supposed to make my delta x tinier? Well, by the limiting process that we just went through, or that you just learned. And so that means that if I take the limit as delta x approaches 0, this x plus delta x will actually be closer and closer and closer to the x, and then the expression will be closer and closer and closer until it actually is the same as the limiting value that would be the slope of the tangent line. So the slope of the secant line is just the difference quotient, but the slope of the tangent line is the limit as delta x approaches 0 of that difference quotient. And that's key. You need to remember that when you're going towards finding the slope of the tangent line, it's the limit as your delta x approaches 0 of your difference quotient. So slope of secant line doesn't have the limit as delta x approaches 0, but the slope of the tangent line does have the limit as delta x approaches 0 of the difference quotient. Let's look at an example. Here we want to use the definition of the derivative to find f prime of x, so find the derivative for the function f of x equaling 3x squared minus x minus 2. So our derivative f prime of x by definition is the limit as delta x approaches 0 of, Now remember, it's f of x plus delta x first in the numerator. So you're going to take all the x's out and put in x plus delta x instead. So 3 times, take out that x and put in x plus delta x, square it, minus, take out that x and put in x plus delta x, and then minus 2. That's your f of x plus delta x. Now it's minus f of x, and f of x has more than one term, so I have to put it in parentheses. So minus that 3x squared minus x minus 2, and this is all over delta x. So that's the limit as delta x approaches 0 of, now remember, you have to use your order of operations. So you have to do your exponent first before distributing the 3 through. Also, it's x plus delta x squared. So this binomial you have to multiply out. Remember, our x plus delta x times another x plus delta x would be x squared plus x delta x plus delta x times x, I'm going to also write as x delta x. Delta x is 2 symbols for one idea, so I need to make sure I realize that's one entity, and then plus delta x squared. So that'll be x squared plus 2 x delta x plus delta x squared when I square this out. Now I'm going to multiply that through by 3. So that'll give me a 3x squared plus 3 times 2x delta x is 6x delta x. And then plus 3 times delta x squared will be plus 3 delta x squared for this part. Now, more than one term, you have to distribute your negative. So that'll be minus x minus delta x. And then I have minus 2, and then again distribute your negative. So that'll be minus 3x squared, minus negative is a plus x, and then plus 2. And that's all over delta x. So that gives me the limit as delta x approaches 0 of, now what you want to do next is to combine your like terms. I have a 3x squared and a minus 3x squared. I don't have any other x delta x's or any other delta x squareds. I have a minus x and a plus x, and I have a minus 2 and a plus 2. So my numerator simplifies to 6x delta x plus 3 delta x squared minus delta x. That's all over delta x. And notice here I have a delta x common factor in the numerator. So I get the limit as delta x approaches 0 of, factor out your delta x. That'll leave me 6x plus 3 delta x. And then remember, minus delta x divided by delta x is a minus 1, and that's all over delta x. And then your common factor of delta x in the numerator and delta x in the denominator, those will remove as a common factor pair. And now when that happens, the limit as delta x approaches 0. Now remember, the delta x is approaching 0. So it's not affecting the x, it's affecting the delta x. So when I look at what the limit as delta x approaches 0 is of 6x plus 3 delta x minus 1, well, it'll still be 6x because 6x is a constant in terms of your limiting variable being delta x. So that'll still be 6x. The limit as delta x approaches 0 of 3 times delta x, well, that's going to approach 0. And then the limit as delta x approaches 0 of negative 1 approaches negative 1. So my derivative for f of x equaling 3x squared minus x minus 2 is 6x minus 1. So I get a function in x that if I put in a specific x value into my derivative, what it generates out is the slope of the tangent to the original function at that x value comma y value from your function. So it's the slope of the tangent to the curve at that x value is what the derivative gives out when you put in an x.